that when something stops, theoretically, it's a theoretical state. When everything stops moving, we call that absolute. Does anybody know what the rest of the word I'm going to say is? Absolute zero. Absolute zero is 0 degrees Kelvin. 0 degrees Kelvin. Kelvin's a K. It's a K. So to give you some idea what it is, 0 degrees Celsius, 0 degrees Celsius is equal to negative 273 degrees Kelvin. So, yeah.
Can you define absolute zero again?
Absolute zero is where everything stops moving. Absolute zero, where everything stops moving, including electrons. Including electrons, just everything. The atom is completely still. That is a theoretical temperature. Remember, temperature is what? A measurement of average kinetic energy. A lot of people think it's a measure of heat. Heat is the energy that heat is energy, and energy is how we measure the ability to move, the ability to have movement. I know it's a weird definition, but in order to move, you need energy. That's it. That's what energy is. Energy is not anything more complicated than that. It's just very ambiguous. It's hard to imagine. It takes different forms, and heat is one of them. All right. But temperature is a measurement of that vibration. Temperature is a measurement of that vibration, of that movement. And when things are not absolutely still, because I don't know of anything that's ever been we've gotten things close to absolute zero, but I don't know of anything that's actually gotten absolute zero. I'm sure it has, and I just don't know about it. I'm not in the in crowd when it comes to science. I only know what I read. Solids have very low kinetic energy. So what are these? What do these balls represent? Molecules or atoms, right? It doesn't have to be a molecule. They could just be a bunch of atoms. But we can call them particles. Can we use the word particles and everybody's okay? So you're right. It can be atoms. It can be, we call them particles. But it doesn't matter really to us in the case of the phase change, whether they're atoms or molecules. They act very similarly, but we can go ahead and think of them as molecules most of the time during this activity. So there are a bunch of particles or atoms, and when they have very low kinetic energy, they settle. I used numerous examples in class to try to help you understand what this is. One of them was the bingo ball or lottery machine. Do you remember that discussion? And if each bingo ball or lottery ball was a molecule or an atom, it was jumping around. When they turned the power off on that machine, what do? They start slowing down, and then finally they do what? They rest at the bottom, settle down at the lowest possible energy state. So this is a solid. That's what a solid is. Just as closely as they can, relatively speaking. Remembering that intermolecular forces can expand this. In most things, they're the densest form. But when you start to involve intermolecular forces, they can do the opposite of what the kinetic energy is doing. So obviously a liquid has more kinetic energy and the gas has the most. So if you were going to label these, I would hope you would have labeled these as solids. Oh, why is this? It's acting up again. Is this power down? Maybe the power in the pencil. Sorry, give me a second. It's a joke. All right. And so these particles are sitting, hopefully they're, you know that they're, oh, now it works? What? The world is against me. All right. Not yet. It might happen, but not yet. So this is solid, this is a liquid, and this is a gas. Hopefully everybody understands that. And often we define solids as the most dense form of matter, but we know with water it's not because of hydrogen bonding. Don't forget it. Make sure it's highlighted and it's in your head on a permanent level. What do we call, I don't like this, there's a heat of fusion and there's melting. So when liquids turn to gas, what do we call that? We call it freezing. When liquids turn to gas, oh, what am I saying? I don't even know what I'm saying anymore. I blame you, Kai. I blame you. When liquids turn to solid, it's freezing. Thank you for correcting it. There's a heat of fusion. And we call it heat of fusion because fusion is when things come together really close. So the heat of fusion, that's why I don't like this. I don't like this thing. Get rid of that, this slash. But there's a heat that's really, when things freeze, when things go from liquid to solid, they release energy. So they have when they go from solid to liquid, they absorb energy. So this is an freezing. Freezing is actually exothermic. They're releasing energy. Something that is freezing is releasing energy. When a solid goes to a liquid, it absorbs energy. But what do we call it when a solid goes to liquid? Solid goes to liquid. What's it called? Melting. And that is absorbing energy. Now, it hurts your brain a little bit, at least it did mine when I was your age, because how could it be absorbed? It's melting. It should be getting hotter. Well, it is getting hotter. It is absorbing heat. It's taking heat into itself. So its kinetic energy is increasing as temperature is going up, but it's actually absorbing that heat. Yeah.
Should we write these notes on drafts?
You can write it wherever you like. You can write right on the diagram if there's room. You can add it to your notes in your notebook. This is a live document. I want you to start thinking about your notebook as this like learning journal that is easy to access, that's well organized and easy to access. And I have to grade these notebooks today. So this is what I have to get through this next. I have to get through this pretty quickly. It's just one of the reasons I'm kind of stressed out over all these interruptions. But in any case, melting, absorbing energy. So energy goes into the solid, the energy gets translated into kinetic energy, transformed into kinetic energy, that solid turns into liquid. We call that melting. When the liquid releases that energy, releases that heat, it turns into a solid since it's releasing it. I'm going to go back to, it's this law of thermodynamics, and often in physics and in chemistry, it's easiest if you just make a square or a dot. And you think there is this law that says energy and matter, by the way, cannot be created or destroyed. So you only have so much energy, period. End of story. So if something is melting, it's increasing kinetic energy. Where's that energy coming from? Yeah.
For melting, would that be endothermic?
Yes. Excellent. Excellent. I was going to say that, but thank you. That would be endothermic. But the question is, why? How do we know the energy is leaving? No, not melting. I'm sorry. Wait a minute. Hold on. I got it right. I was looking at the arrows were in there. So when something's melting, it's absorbing energy. It's endothermic. When something's freezing, it's releasing energy, it's exothermic. How do we know that? Because energy can't be created or destroyed. And if this thing has very little kinetic energy, low temperature, and it increases in temperature, increases the movement of the particles, then and becomes a liquid, then it must have taken energy in, because it had to come from somewhere. Where'd that energy come from? Outside itself. So when you touch that table, it's cold. The heat is leaving you and going into that table. That table's gaining energy. Where to get its energy? From you. When you step outside in the cold wind and you get cold, you're losing energy. Your molecules are moving less. And the wind is gaining heat, gaining energy, and it's moving faster. So that's how this works with melting and freezing as well. Now, when going from a liquid to gas, what do we call that? Vaporization. The word is vaporization. There it is. Vapor. You know what vapor is. You guys have vaping all over the place, unfortunately. Please remember, vaping is horrible. They're doing the same thing that the cigarette companies did in my parents' age and my group. So vaporization means going from a liquid to a gas. Turning something to a vapor means you're vaporizing something, means you're turning it into a gas. So there's a heat of vaporization. With each of these, there's a certain amount of energy that's required to make it happen. So we call this the heat of vaporization. We actually just do HV. This heat of fusion, another is HF. And this, well, that's it. That's good. That's right. That's an F. I don't know, it looks like I don't even know what that looks like, but it is an F. Yeah. Yeah. So when a gas turns into a liquid, what do we call that? Condensation. All right, condensation. So now you can fill this chart out. I think you can self-check and make sure you get those right. And again, I think that's good, right? We're all good with this page? Yes? All right. Everybody in here, if I give you any of these questions on a test, heat of vaporization, is it an endothermic or exothermic reaction? This is where you're going to get confused. Let me point this out. Let me point out that this is where you're going to confuse. Which one of these is exothermic and which one's endothermic? That's going to confuse you on a test. If you don't know it straight, if you don't have it in your head solidly, you're going to get on that multiple choice question. You're going to reverse them. That's it. I know that's coming for some of you. So you have to put some extra effort in making sure you have that straight. All right, moving on. Now I saw a bunch of graphs today that were backwards, and I think the reason is you didn't know what the axes were. So when we're graphing, as we discussed in the past, you have to know what is the independent variable and the dependent variable. If you don't, If you don't, you're going to get confused. And it could do all kinds of things. What I saw this morning was at least 5, and I'm expecting 90% of you reverse this graph. When you graphed it on the last page, instead of drawing a graph that looks like this, you had the opposite and went the opposite way. It's easy. It sounds silly, but it's actually very easy to do if you don't get your axes correct. You have to know what the heck you're graphing. If you're just drawing a line on a piece of paper, then it doesn't make sense. And it could go any way. I could put a line this way, vertically. I mean, I could put it anywhere. You have to understand what you're graphing. So the x-axis in this case is heat. Because how do I get something to go from a solid to a liquid? Oh, is that right? Solid. I think E is, to a liquid to a gas. How do I get it to go? Let me say if this is the solid and the green line, how to make it go into a liquid, the blue line, and then how do I make that go to a gas, the yellow line? How do I make them do that? I have to do what?
We have to add heat.
Add heat. I have to give it energy, the energy of movement. Energy is the stuff of movement. So I have to give it heat. So what am I measuring in a graph like this? I hope you know I'm measuring the temperature. I'm measuring the temperature. But wait a minute, I'm adding heat. Why am I measuring temperature? How can I see the confusion? The confusion is some of you still have in your brain, and you're going to have probably after you leave this class, it's still going to be the case. Some of you have in your brain that temperature is a measurement of heat. It's not. It's not. It's a measurement of kinetic energy. So this is temperature. Degrees Celsius. Yeah. So who needs it? I thought I swear I bet you there's some over here. Look over here. I bet you they're right there. Make sure there's a graph on the back of it. So when I look at a solid, liquid, gas, remember temperature is a measurement of change in heat. Change in heat. Did you do this? Did you upload it? Yeah, yesterday? Did you upload the updated version? Because it was due today. If not, you're not. Okay, just asking. I don't know what else to say. All right, so solid, liquid, and gas. This is heat. This is temperature, degrees Celsius. As I add heat, what happens to this material? Well, it gets hot. The temperature goes up. As I add heat, the particles start to move faster and faster. They're still solid. They're just vibrating faster and faster, moving back and forth faster and faster until they reach a point. What that point is, I don't know. It depends on the substance. What temperature is this? It depends on the substance. But it's a point where the temperature doesn't go up anymore. Yeah. Say what? That's right. It's exactly what's happening. It's going from a solid to liquid. So this would be the melting point. And what is C? If I did C in a yet one more color, let's go ahead and use this color. Here, this is a bright color. C is, what does this line represent? This amount of heat. From here to here is a certain amount of heat. Call it 100 joules, 1,000 joules, whatever. What is that heat? Yeah. Not vaporization, it would be the heat of fusion, which is the heat required to either melt it or freeze it. But that's regardless. There's something. What is actually happening here? Why is it taking this much energy, whatever this is, right? Let's call it 100 joules. Why is it taking 100 joules to move from here to here before it can change? And before they can start moving faster again. Yeah. That's right. They're going to break, let's call them intermolecular. Bonds are being broken. The stuff that holds the substances together. There could be ionic bonds at that point as well, but just because this is biology, let's just call it intermolecular bonds. So the bonds that hold the molecules together have to be broken before they can move any faster. They can only move so fast while they're still holding on to each other. Am I making sense? So this is the energy required. This is it. It's also called the heat of fusion. And what's happening over here, from here to here, from a liquid to gas, is called what? Vaporization. And then as you're vaporizing something, there's a certain amount of energy that's required before the temperature gets any hotter. This is exactly what you're doing. You're breaking. That's right. In biological systems, you're breaking the hydrogen bonds, but we'll just go ahead and call them intermolecular bonds. There are numerous types of intermolecular bonds. We're just covering hydrogen bonds because we have a limited amount of time really to discuss this, okay? So they're intermolecular bonds. We need to break the sticky stuff that holds them together. So this energy, this is going to be more in water than it would in alcohol. Yeah? Yeah, I know. There's nothing I can do about it. It shuts itself off. I didn't push any button, I swear. This is you see what I go through do you blame me if I start screaming in the middle of the class? Yeah. Who said yes? I can't win in this place. Of course, you're going to turn off. Just randomly turn off by yourself. Go ahead. Nobody cares. You got all the time in the world. These kids can do all this for homework. Now all of a sudden now you're going to scream. Yeah. All right, so vaporization. Liquid, vaporization, gas. So this is the energy required for it to go from liquid to gas. This amount of energy is high in water relative to alcohol. This is high in water relative to acetone. So you go in a nail polish shop, what's the first thing you smell? Acetone. Why do you smell acetone? Nobody's drinking it. It's in the air. Why is it in the air? Because what's low? What's a very small amount of energy required? Very small amount of heat to do what with acetone? To vaporize it. It vaporizes very easily. The vaporization energy for acetone is very small. So at like 70 degrees or 60 degrees at room temperature, it's a gas. And you leave a bowl of acetone out, it's going to go into gas form at very low temperatures. So that's why acetone in a room by the way, they should really vent those places better. You should not be smelling that much acetone. My wife gets her nails done. Every time I go in there, I'm like, you guys are going to get sick. All right. Really, be careful with acetone. It's not good to breathe that stuff in. Huh? You have to wear actually a gas mask with carbon filters. The masks that they wear, those cloth masks, like the ones we use to stop COVID, are useless with gases because it's a gas. If you can breathe oxygen through the mask, then you can breathe the gas. You need a carbon filter that's going to absorb that volatile gas. So, anyways, enough lectures. So we get this. We're okay with this. Everybody got it? All right. So moving on. 3. There's 3 different substances. Let's take a look at the heating curve for this material. The heating curve for water is this. This is 5. The heating curve for this is 5. I don't even know. Is that chlorine? NaCl. Looks like it's about 5. It's just a little lower. Oh, they're putting time. That's why you guys put time in minutes. But what is it really? They're keeping the heat constant. It's really heat added. I don't like that they put time. They should just put heat added. All right. And here is how much can water really absorb in how much heat can water absorb and not change temperature as compared to the rest of these? And not change temperature. Like is water doing the best at absorbing heat and not changing temperature? It looks like gold is doing a pretty good job, right? Gold gets really hot though. It melts at 1,000, and then it vaporizes at 3,000. Sodium does pretty good. So these must have really good what? Really strong bonds, really strong sticky inner. These aren't molecules. This is what are called metallic bonds. You don't even want me to start talking about it. You'll learn it in chemistry. And this is that NaCl, that full ionic charge, the salt, the attraction between. So these are very strong bonds. But of molecules, molecular bonds, which one did a better job? Water or chlorine gas? Water. Water absorbed 200 degrees before, in the same amount of time, went to 200 degrees. Chlorine could only absorb 100. So as far as molecules go, water... molecules, remember, are sharing electrons. Water does a really good job at absorbing energy. Yeah.
So to really determine the strength of these bonds, you could say that like measuring the steepness and length of the segments going from solid, liquid, and gas.
Yeah, it's very useful, right? Like when you look at here, this changes temperature really quickly. Do you see that? Even water, even at gas form, it's a slower slope, a shallower slope. It changes temperature less quickly. That's why we say water has a lot of ability to absorb energy. That's one of the qualities of water. So it makes it a perfect solution for life. It makes us stable. When it gets cold outside, we don't have to freeze. When it gets hot outside, we don't have to boil, right? And part of it is that water absorbs so much of that energy without having to change temperature. We're very stable. It's really the perfect solvent for life. Does that make sense to everybody? I mean, it's really kind of humbling to think about it. All right, I think you guys could have answered the answers to these questions. I just wanted to point those out. Now, you were supposed to graph this, and what I saw people do was this. All right. That was wrong. And they labeled it correctly. They labeled the graph correctly. Good job. But they just reversed it. Okay? So be careful with that. Be careful. Read the graph. First thing you start with is what are you putting on the X? Well, it's time. Now I understand why people put time, but it's actually heat. All right? It's the time that you're heating the substance. So don't get confused about that. Yeah?
Isn't it the opposite of heating curve though? The cooling curve. Were we supposed to go with it?
Oh, I don't know. What is it? Is it cooling?
Yeah, it's the opposite.
I'm so sorry. See, I make mistakes too. I blame Kai. So, anyways, it is the cooling curve. It was supposed to be opposite. My bad. Those of you who did it right, I did it wrong. Again, pay attention to details. There you go. You guys did it right. My bad. Yeah. So, anyways, yeah. It's still, though, heat is still on the, or time is still here. And it is still heat. But now it's not how much you're heating. It's what is it? How much heat is not going into it. It's how much heat's what? Coming out. So this is an exothermic reaction. Water would cool very slowly. So you guys were right. My bad. Seriously, I'm embarrassed. But anyways, go down. Come across. Should look something like this, okay? All right? One thing I did notice, I hope I didn't get wrong again, but I did notice that some people did this. Oops. What's wrong with that? Assuming that the line, yeah. That's right. You want to use up the whole graph, guys. You want to use up the whole graph. How can you do that? Well, you look at 0 to 120. So it should go from 0 here. You can go below 0. Maybe you want to see what do we use graphs for? What are graphs used for? To do what with data? Analyze it. Right, analyze it. Collecting it, we already did that. There it is. There's collected. Now we got to analyze it. We use graphs to predict. Write that down. Predict. Predict what is happening outside of our data range. We know what happened here. We know what happened at 0. We know what happened at 30. We know what happened at 60. We know what happened at 90. We know what happened at 100. And we know what happened at 120. But what's going to happen at 150? What's going to happen at 200? What happens at negative 50? We can extend the line and predict. That's the advantage of graphs. They're really amazing. So what do you label your axes? It depends on your intent. So if you want to just see what's going on in between 0 and 120, then you would label this 0, and your max would be 120. However, what if you wanted to know what's going to happen at 150? So I'd put 150 out here. And over here, I might still keep it at 0, or I might make it negative 20. So it's all up to whatever it is I want. A lot of us get trained that this always has to be 0, 0. It does not have to be 0, 0. This could be anywhere on a graph. Does that make sense? All right, so let's go ahead and keep it at negative 20 just for argument's sake. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have 20, hear my words, I have 20 divisions. Do you agree with that? I have 20 divisions on the x-axis. 20 divisions. What's being divided 20 times? Yeah. The time. But how much is there? How much time is there? 150 plus what? 20. 170 total. So I have 170 total. So how do I divide that? What am I going to divide it by? 20. Somebody want to do that math? Yeah, have your calculators out. What is it? 8.5. 8.5. Keep your calculator out. So each of these divisions is 8.5. So put negative 20 plus 8.5. What is it?
Negative 11.5.
What?
Negative 11.5.
Plus, what was it? 8.5? Go ahead. What is it? What is it? Negative 11.5 plus 8.5. What is it? Anybody? Do the math. Huh? Negative 3. Plus 8.5. What is it?
5.5.
Plus 8. Go on, continue.
14.
Go. Yeah. Go.
39.5.
Next.
What is it? 40. Would it be 48? Yeah, that's 48.
Next.
56.5.
56.5. What is it? He's good. What is it?
The next was 65.
Next was 65?
73.
This,
Oh, I know,
this
yeah,
one
it
is
would,
56.5.
Because they just multiply
All right, next. What is it?
65.
Next.
73.5.
Next. Huh?
It's 78.5.
73.5, then what?
Then it would just be 82, yeah. And then 90.5. 99.
What is it? 107.5? That's a good radio station. Next.
160.
Ne- One what?
24.5.
Next.
41.5.
And then 150, right? That's how you do your axes. It's just that simple. With a calculator, it's easy. Just take what is the total number that you want to divide, then count up how many you divided. So with temperature, why don't we, all right, so that's fine. Temperature, we can just go ahead and start at 0 and then move up to whatever it is because that's the temperature we have. But why don't we start at -10 because I think that would just be more interesting. And really, if you're thinking about time, does it make sense to have -20 time? It doesn't really make a lot of sense to have -20 time. Right? But we can have -20 heat, right? So just wanted to show you how to do that. So just get rid of that. All right, so 120 divided by 20 is what? What is it?
13.
So it's 13, 26, etc. And then when you do your y-axis, it'll be temperature, and we'll start at 0, and it's 10, 20, 30, 40. So it's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40, 50, and 60, 70, 80, 90, 200. So that's not even enough. I can't do it by 10. I have to do it by what? 5, right? I could do all that. But sometimes I just want to do it easy. You know what I'm saying? So we could just start at 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. You know what makes this a lot easier? Excel. With Microsoft Excel, I just have to put the data I have and it graphs it for me. Excel. You have access to it. Did you know you have Excel? You have it you have access to it through Cleveland. Yeah. Yeah. Yeah, that's not working either.
I have all the numbers for 12.5.
Oh, did I mess it up? I'm distracted by trying to do too many things at once. I apologize. If this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 250 divided by 20 is what?
12.5.
12.5.
Here's the numbers.
Oh, you already got them. What's the next one?
25.
So let's just go with 25. Give me every whole number. The second one's 25,
Fourth one's 50.
50.
75 for
This goes up by 25.
All right, so 100, 125, 150. Every other one, right? 175, 200, 225, and 250. So I know this can be confusing to you, especially those of you that are having conversations and worrying about your chains and all that. And when you're worried about, when it can get confusing when you're trying to number these things on a test. You won't ever have a standardized exam where you have to actually create your own graph. They used to do that in AP tests. But you do have to read them. And so reading the axes, it's really good practice to think about what a graph is. So this is exothermic, and I was thinking it was endothermic. I was thinking it was absorbing. I thought it was melting, and and instead this is freezing, right? This is the cooling curve, not the heating curve. So we start at zero. At 0 time, we're going to start at 250. So you see how I'm filling up the whole chart. At 30, which I'm not sure where it is because I didn't number it correctly.
30 is 1.175.
How many slashes?
It's right above. It's right above.
No, the x-axis. Give me the whole numbers on the x-axis.
3.
3 is where? Second hash, third hash. Third hash is 3.
30.
It's 30.
Third hash 30.
All right, what's the next whole number?
It says 1.75 at 6 hash.
You have every 4 dashes is 30. Is that correct? Isn't that what you have there?
Every 3 dashes is 30.
Every 3 dashes is 30? All right,
Sorry.
30. 1, 2, 3, 60. 1, 2, 3, 90. 1, 2, 3, what is the third one? 120. 1, 2, 3 is 150. 1, 2, 3, 80, thank you, 180. And the last is 210, which isn't there because I messed that up, I don't know, whatever. So if I go 30, the next one is what? If the time is at 30, I should be at 175, something like that. At 60, I should still be at 175. At 90, I should be at 22. It's a big drop. Somewhere around there. And at 100, I should be 22. 100 should be somewhere around here, somewhere. And 120, I should be at 10. And so the line should be drawn something like that, and that, and that, and that, and then that. Right? Now, if I really wanted to make this graph fill out so I could use it, I would probably made my biggest number at 120. So this would be 120 like we had discussed, and then they'll fill out the whole graph. Does that make sense? Yes or no?
Yeah.
All right, so I just wanted you to see that with graphing. All right, so we got our data. You see it's cooling. You see heat. Where's all this heat going? So this is the temperature, and this is the time. Over time, it's losing heat. Where is it going? Environment. All right. All right. Now, your job today.